Okay, today we're going to talk about energy, and we're going to be looking at how we can make measurements with energy. Some of this initial part will be a little bit of review, but it is important to understand in how we apply this to what we'll be doing in the lab. So you might remember that energy can be converted from one form to another, but may not be created or destroyed. And when we looked at this, we looked at some examples like riding a bike, driving a car, or fireworks, and we looked at how the energy was transferred between potential and kinetic in each of these cases. What we'll be seeing today and applying in the lab is that we can do this when we have temperature changes between objects. When we have these sorts of changes going on, we want to be familiar with what we call a sign convention in terms of where is the energy going. And we define energy as being positive when it goes into a system and negative when it comes out of a system. We call this an exothermic process when the energy is coming out of something. So something that is losing energy is exothermic. Something that is gaining energy is endothermic. The lab will be discussing, we have one thing is losing energy by the temperature going down. One thing is gaining energy by the temperature going up. So we could apply this idea of the endothermic thing is the thing that's gaining that energy. The exothermic thing is the thing that's losing that energy. In order to do this, we need to be able to measure the energy. And energy is something in science that we can measure, and we have units for it. The SI unit of energy is the joule, and the joule is defined as a kilogram meter squared per second squared. So that we're not going to be really using this quality too much in here. This is more of something you would use in a physics course. But I wanted to point this out so that you see that the energy we're measuring isn't some abstract concept. It is actually directly related to some of these other things that we have measured in class, or we can understand how we would measure these other sorts of things. There are other ways we can measure energy. We have what's called the calorie. This measure of energy is the energy necessary to raise exactly 1 gram of water by 1 degree Celsius. And because it is measuring energy, we can have a conversion between calories and joules, and that is shown here. 1 calorie is equal to 4.184 joules. That is an exact conversion. It has an unlimited number of significant figures. Now some of you are seeing this word calorie and you're thinking of your food, because on your food there's often, it says how many calories that food has. That is actually not the same thing. That is what's called the nutritional calorie. So when you see on your cereal box or your coffee order at a Starbucks, if you see a certain number of calories on that, that is the nutritional calorie. That is supposed to have an uppercase C. It's not the same as the lowercase c calorie we looked at up here. The nutritional calorie is actually a kilocalorie. You have 1,000 of those. So the calories on your food are actually 1,000 times bigger than you think they are. So instead of saying 1 gram, if we said this is 1 kilogram by 1 degree Celsius, that would be what we would measure with this nutritional calorie. Another measure of energy is the kilowatt hour. So after a summer of 105 degree weather for weeks on end, you might be familiar with this based on your power bill. A kilowatt hour is a measure of energy. It's a large measure of energy. A kilowatt hour is a little more than 3.5 million joules. So a lot of energy in a kilowatt hour. For this class, we're mainly just going to be using the joule. I did want to go through and look at some of these others because they are all measuring energy. They're all measuring the same thing, and some of these are things we're familiar with from other aspects of our lives. So I want to kind of highlight that these are measuring the same thing, and we pick them based on, maybe what is appropriate for the amount of energy we're measuring. For measuring a lot of energy, kilowatt hour would be a good thing to use. If we're measuring energy content of food, the nutritional calorie is appropriate, and the small amounts of matter we typically use in a chemistry lab, the joule is more appropriate. So we'll mostly be using this one, but I wanted to talk about these others because I know many of you are already familiar with them a little bit, and they are talking about the same kind of thing. Okay, so how we're going to use this in our lab is with the idea of heat capacity. And the heat capacity of something is the energy necessary to increase its temperature. So some things are easier to heat up than others is the basic idea here. We're showing, it looks like somebody's going on a picnic and they put all their food in this cooler to keep it cool until they're ready to eat it. And in order to keep it cool, we usually put some ice in there. We don't go to our freezer and take out a big block of iron or lead and put it in the cooler, partly because the heat capacity of these metals are very low compared to the heat capacity of water. Water is very, very good at storing energy. And we can illustrate that in a couple of ways. One example is that we live in at least the Central Valley is a fairly dry region, and because of that, the temperatures can be fairly extreme on occasion. So I mentioned the 105-degree weather we've had throughout the summer. If you go to the beach, it's usually not going to be 105 at the beach. And the reason is because there's a lot of water there, and that water helps to moderate the temperature. So the water is keeping the temperature from getting too high. An even more extreme case of this is if you go to another planet. If you look at other planets, their temperature changes will be in the hundreds of degrees from night to day because there is not as much water there. So the fact that we live on Earth allows for a fairly moderate change in temperature compared to some of the other planets. Another example is the human body. The human body is mostly made out of water, and the human body has a very small range of temperatures in which it can operate well. So even if we go into more extreme environments, our body temperature does not change very much. And that's because the water is able to help regulate that. So water has a very high specific heat capacity, and that high heat capacity is something that allows us to maintain temperatures, whereas some of these other things will change temperatures very quickly in comparison. Heat capacity is a property of a substance, so we do want to know that we can look it up on this kind of table and use it to do calculations, and we'll see some examples of that here. Okay, the main calculation we're going to use this with is the heat equation, and we're showing the heat equation here. The heat equation is Q. The lowercase letter q is used to represent energy in the form of heat. We've seen M before to represent mass. This uppercase C is the heat capacity, so that is the thing we just saw on the previous table. It's saying here heat capacity, this would be a specific heat capacity based on what we saw on that table. And then the last thing we see here is this triangle symbol and a T. This triangle is the Greek letter delta. We use the letter delta to represent a change. So this is showing a change in the temperature. And the change in the temperature is how we are able to know how much heat is exchanged when we use the heat equation. I want to talk a little bit about this in terms of how it works. This is a little bit more involved than some of the other math we've looked at so far. And the reason for that actually has to do with the units of the heat capacity. I'm going to go back to the previous slide for just a minute. If we look at the units of specific heat capacity, they are joules per gram degrees Celsius. When we had, for example, density, the units were grams or mass per volume. So this is a little bit different in that it has 3 units instead of just 2. And what that means is that when we when we use this measurement in an equation, we need to cancel out more things. So that's why we have more things here. And as we'll see, the units are still going to tell us how to solve this problem. Okay, so here's an example. A layer of copper on a pan has a mass of 135 grams. How much heat in kilojoules will raise the temperature of the copper from 26 degrees Celsius to 328 degrees Celsius? Okay, so this is our example. So what we want to do is we want to get some information here. We see the mass is 135 grams, so we have that information. We have a temperature change, so this is our initial temperature, and this is our final temperature. So between those we can find the delta T. The other thing we would need to know is the heat capacity, and we're not given the heat capacity in the question. So what we would need to do, we would go back to this table and we would look for copper, and we see copper has a specific heat capacity of 0.385 joules per gram degree Celsius. So we would have to know, we go look that up on the table if it's not provided. Okay, so let's see how we solve this problem. Okay, so here we're showing the given information, so we've written that down. Here we're showing specific SH for the heat capacity. We're showing how to calculate the delta T. So how we do this is we take the final minus the initial, and that difference is delta T. And then we put everything into the heat equation. So we've got the mass times the delta T times the specific heat. And we can see the units cancel, grams are canceling, degrees Celsius cancel, and then we convert to kilojoules, so the joules cancel. So this is just the same kind of conversion that we did in chapter 2 with the kilo prefix. Okay, so that's how we would do that. That's how we would use the heat equation to find the amount of heat that something, in this case something, the copper was gaining that heat. Okay, so how we use this, how we use the heat equation is with that law of conservation of energy. So energy is never lost. Energy can be transferred between objects. What that means is that if something is losing energy, something else is gaining that energy. So we can take those two together, and we can take the heat equation from one thing and say, maybe equate that to the heat equation for something else, if we know that all of the heat lost from that one thing is going into the other thing. So we can define a system and surroundings as two things in contact with each other where heat is flowing. And as we'll see, we often will have the system and surroundings will end up at the same temperature, and they will have the same final temperature. You'll notice there's a negative sign here. Anytime you do this, anytime you have Q of one equals Q of another, you'll have a negative sign because one thing is losing and one thing is gaining. So the negative sign is helping us to keep track of that. Okay, so I want to do one more example. This example is very similar to the example that, or to the problem you'll be doing in the lab. What I'm going to do, I'm going to have a separate video for this example. So what you can do, you can maybe take a look at this, see if you can solve it. Once you've given it your best shot, go ahead and watch the other video.